Almost everything you can see in the universe has weight, yet almost none of that weight comes from the matter you imagine. The atoms in your hands, the screen in front of you, even your own body. About 70 kilograms, roughly 154 pounds. Owe their mass to something you have never seen, never touched, and can never isolate. Tonight we step directly into that unsettling fact. This story is about the gluon, the particle that carries the strong force, binds quarks inside protons, and quietly decides how heavy the visible universe becomes. Inside a single proton, experiments show that less than 2% of its mass comes from quarks themselves. The rest emerges from trapped energy, relentless motion, and confined fields. To understand why nearly all visible matter exists at all, we begin where mass truly forms. In Part 1, why does almost all visible mass in the universe come from something you've never seen? Almost everything you believe gives matter its weight turns out to be almost irrelevant. Inside the proton, the building block of every atom you have ever touched, less than 2% of its mass comes from the rest mass of its constituent quarks. This is not an approximation, not a philosophical provocation, but a result measured repeatedly in high-energy scattering experiments and confirmed by large-scale numerical calculations. The remaining 98% emerges from something far less intuitive energy stored in motion tension and fields carried by particles called gluons. To understand why nearly all visible mass in the universe exists at all, the story must begin here, in a space smaller than a femtometer, where the rules of everyday matter quietly collapse. In the early 20th century, physicists believed mass was an intrinsic property, a kind of solid accounting number attached to particles like an immutable label. A proton was assumed to be heavy because its constituents were heavy. That picture survived only until experiments grew precise enough to probe the proton's interior. In the late 1960s, deep inelastic scattering experiments at the Stanford Linear Accelerator Center fired high-energy electrons into protons and watched how they deflected. The results were unsettling. The proton did not behave like a simple bag of three massive objects. Instead, it responded like a turbulent system filled with moving, interacting components. Momentum was distributed in unexpected ways, and much of it appeared to belong to particles that carried no mass at all. Those particles were gluons. They are the carriers of the strong force described by quantum chromodynamics, or QCD. Unlike photons, which transmit electromagnetism and largely pass through one another without interaction, gluons interact intensely with each other. They bind quarks together, but in doing so they create a dense, restless field of energy. This field is not static. It is constantly fluctuating, stretching, compressing, and rearranging itself inside the proton. According to Einstein's relation, E equals mc squared energy contributes to mass. In the proton, it is this energy, motion and confinement combined, that dominates the mass budget. Richard Feynman once remarked, "It is important to realize that in physics today we have no knowledge of what energy is." The statement was not an admission of ignorance, but a warning against naive pictures. Energy is not a substance. It is a property of systems in motion and interaction. The proton is a vivid example of this principle. Quarks inside it are nearly massless by everyday standards. The up and down quarks that define ordinary matter have rest masses of only a few mega-electron volts, yet the proton's mass is about 938 mega-electron volts. Where does the difference come from? It comes from gluons and the relentless dynamics of confinement. Confinement is one of the most counterintuitive features of the strong force. Pull two electrically charged particles apart, and the electromagnetic force weakens with distance. Pull two quarks apart, and the opposite happens. The gluon field between them intensifies, storing more energy the farther the quarks are separated. This behavior is not a metaphor. It is a consequence of the non-abelian nature of QCD, where the force carriers themselves carry charge. Gluons interact with gluons. The field resists being stretched, like an elastic band that stiffens rather than snaps. Attempt to isolate a quark, and the energy you inject into the system materializes as new quark-antiquark pairs. The proton refuses to fall apart into simpler pieces. This refusal has measurable consequences. When high-energy collisions at CERN or other accelerators probe protons at increasing resolution, they reveal that gluons carry a large fraction of the proton's momentum, especially at small distance scales. The proton begins to resemble a storm, more than a solid object with energy flowing continuously among its constituents. In this environment, mass is not something added up from ingredients. It is something generated by motion, constrained by force. The importance of this mechanism extends far beyond particle physics. When cosmologists speak about visible matter or baryonic matter, they refer to matter made of protons and neutrons. Measurements of the cosmic microwave background, observed in exquisite detail by missions led by organizations like NASA and ESA, allow scientists to infer the density of this matter in the early universe. These measurements do not count protons one by one. They infer mass density from how ordinary matter interacts with radiation in the first few 100,000 years after the Big Bang. What they are indirectly weighing is largely gluon energy locked inside nucleons. This connection becomes clearer when we look back to the first microseconds of cosmic history. At temperatures exceeding 2 trillion Kelvin, matter existed not as protons and neutrons, but as a quark-gluon plasma. Experiments at heavy ion colliders recreate this state on microscopic scales, confirming that quarks and gluons behave as a collective fluid at extreme energy density. As the universe expanded and cooled, gluons confined quarks into hadrons. In doing so, they froze vast amounts of energy into mass. The mass of every future atom was set not by the bare quarks themselves, but by the dynamics of the strong force during this transition. One might ask whether this picture is speculative, dependent on models rather than proof. For decades, that concern was valid. The equations of QCD are notoriously difficult to solve at the energy scales relevant for protons. Analytic solutions are impossible in most cases. The breakthrough came from computation. Using lattice QCD, physicists discretized spacetime into a finite grid and simulated quarks and gluons directly from the fundamental equations. These calculations required supercomputers operating for months at a time. The result was decisive. The proton mass emerged naturally from gluon field energy, with quark rest masses contributing only a small correction. The numbers matched experimental measurements to remarkable precision. This convergence between theory, experiment, and computation is one of the quiet triumphs of modern physics. It demonstrates that the mass of ordinary matter is not an arbitrary parameter, but a consequence of well-tested laws. It also reframes the question of what matter is. The solidity you experience when you press your hand against a table is not primarily due to massive particles sitting still. It arises from dynamic fields resisting compression from energy confined so tightly that it manifests as inertia. The implications ripple outward. In neutron stars, where matter is compressed to densities exceeding those found in atomic nuclei, gluon dynamics may again reshape mass and pressure relationships. Observations of neutron star mergers through gravitational waves detected by observatories supported by NASA and international partners provide indirect tests of strong force physics under extreme conditions. Xiaoyu Jinghao Ling. 5# is greater than here. Nuclear theory and astrophysical observation meet bound together by the same gluons that define the mass of a proton. Yet there is a boundary to what gluons can explain. They dominate the mass of visible matter, but they do not account for dark matter, which interacts gravitationally, but not through the strong force. This distinction is crucial. It tells us that while gluons explain why ordinary matter is heavy, they also define the limits of that explanation. The universe contains more mass than gluons can provide. Understanding what lies beyond that boundary requires new ideas, but recognizing the boundary itself is already a profound insight. Frank Wilczek summarized this realization succinctly. Most of the mass of ordinary matter is not due to the Higgs mechanism. It arises from the energy of confined quarks and gluons. The statement is not a dismissal of other mechanisms, but a clarification of hierarchy. Gluons are not exotic add-ons. They are the primary source of the weight of the world, you see. If mass, the most familiar property of matter, emerges largely from invisible fields and motion, then what does it really mean for a particle to be massless? And how can something without mass end up shaping the weight of everything you touch? Part 2. Why are gluons massless, yet responsible for the weight of everything you touch? Your body has mass, the floor has mass, the earth has mass, and yet the main source of that mass inside ordinary matter comes from particles that have no rest mass at all. If that sounds like a contradiction, it is exactly the kind of contradiction that modern physics learned to treat as a clue. Gluons, the carriers of the strong force, are massless in the same precise way that photons are massless, and still they are central to why a proton is heavy, why atoms have weight, and why the visible universe is not made of almost nothing. This part stays close to the measured facts, and it takes you into a place where mass stops being a simple ingredient list and becomes something created by confined energy. Start with the most concrete number in this story. A proton has a mass close to 1 atomic mass unit, about 1.67 times 10 to the minus 27 kilograms. That is the mass scale behind the weight of ordinary matter, because every atom's nucleus is built from protons and neutrons are only slightly heavier than protons. The puzzle is that the quarks inside a proton are light. If you add the rest masses of the 2 up quarks and 1 down quark that define a proton, you get only a small fraction of the proton's full mass. The rest is not missing. It is present as energy stored in the strong interaction itself, mostly in gluon fields and in the motion that those fields enforce. Frank Wilczek describes this directly in his essay Origins of Mass, writing that most of the mass of standard matter by far arises dynamically from back reaction of the color gluon fields of quantum chromodynamics. His Nobel lecture makes the same point in even sharper form, emphasizing that the mass of ordinary matter derives almost entirely from energy, specifically from the energy of massless gluons and nearly massless quarks. So why are gluons massless in the first place? The answer is not that gluons are too small to have mass. It is that the strong interaction is built as a gauge theory, and in the simplest unbroken form of that theory, a rest mass term for the gluon field is forbidden by the symmetry that makes the theory work. Put in plain language, the mathematics that keeps the strong force consistent also locks the gluon into behaving like a massless carrier. A concise statement of this appears in standard discussions of Yang-Mills theory, where gauge invariance forbids a mass term in the Lagrangian, and therefore the gluon is treated as massless. This is not a philosophical preference. It is a structural requirement of the theory, as used to describe high-energy scattering data. Massless does not mean powerless. It means that a free gluon would travel at light speed and would not carry a rest mass energy when it is isolated. But in nature, gluons are not found in isolation. They are trapped by confinement, and confinement changes what energy looks like. the strong force does not behave like electromagnetism where fields spread out and weaken with distance. In QCD, the field lines between color-charged objects tend to bundle into a narrow tube. As you try to separate quarks, the energy in that tube increases rather than dissipates. The system responds by converting that energy into new quark-antiquark pairs before allowing an isolated quark to emerge. That is why a proton does not come apart into free quarks, the way a molecule can come apart into atoms. It is also why a proton can store so much energy inside such a small region of space. Now bring in Einstein's relation in the most useful way, without symbols. In special relativity, energy and mass are two ways of describing the same physical quantity. If energy is trapped in a system that cannot easily escape, that trapped energy contributes to the inertia of the system. Inertia is what you feel as mass when you try to accelerate an object. A proton is precisely such a system. The quarks inside it move, not because they are orbiting like planets, but because quantum mechanics does not allow them to sit still in a tiny volume with a well-defined position and momentum. Their motion is tied to gluon fields, and those gluon fields carry energy. The combination of motion and field energy is not a side detail. It is the dominant term in the proton's mass. A useful way to keep the logic straight is to separate three ideas that are often blended together in casual explanations. First, the rest masses of the quarks are real and are linked to the Higgs mechanism in the Standard Model. That contribution matters for many phenomena, but it is not the main source of the proton mass. Second, gluons have no rest mass, but they carry energy and momentum, and they also carry color charge, which makes gluon-gluon interactions intense. Third, confinement prevents the strong field energy from dispersing, so the energy stays inside the proton as a permanent part of the object. When you put those together, the apparent paradox becomes a measured mechanism. Massless carriers can still produce massive bound states, because bound states weigh not only their ingredients, but also the energy required to keep those ingredients confined. This is where the historical story becomes important, because it shows that the conclusion did not come from a single clever argument. It came from decades of experiments and a slow tightening of evidence. In the 1960s and 1970s, deep inelastic scattering transformed the proton from a small, hard ball into a complex, evolving structure. Electrons fired at protons at high energies did not scatter as if the proton were uniform. They scattered as if there were smaller constituents inside, carrying fractions of the proton's momentum. That part of the story led to the parton model and then to QCD. Over time, experiments revealed that gluons carry a large share of the proton's momentum, especially at small momentum fractions, in high-energy regimes where the proton's interior looks increasingly gluon-rich. Then came direct signatures that gluons were not just bookkeeping devices. In electron-positron collisions, certain event shapes, like three-jet events, provided strong evidence for gluon radiation, and for gluons behaving as real quantum objects that can be emitted and detected indirectly through the patterns of hadronic jets. By the late 1970s, collider experiments at DESI helped establish gluons as part of the working inventory of particle physics. The picture that emerged was not that gluons are visible as isolated particles, but that their effects are measurable in the structure and outcomes of collisions. Still, measuring scattering patterns is not the same as calculating mass from first principles. For that, physics needed computation. Lattice QCD is the idea of taking the continuous space-time of the equations and approximating it as a grid, then letting quark and gluon fields evolve according to the theory, while a supercomputer performs the enormous bookkeeping. The goal is not to fit a curve to data, but to start from the equations and see whether hadron masses come out with the right values. Over the last few decades, lattice QCD calculations have become accurate enough to reproduce hadron spectra and to separate contributions to the proton mass in a controlled way. This is one reason Wilczek's phrasing is so confident. The theory of quarks and gluons does not merely accommodate the mass of the proton, it generates it. At this point, it becomes possible to say something very concrete about the weight of everything you touch. Take a human-scale object. If a person has a mass of 70 kilograms, most of that mass is in nuclei, and most of nuclear mass is in protons and neutrons. In a basic accounting sense, your mass is largely proton mass, and proton mass is largely strong interaction energy. So it is accurate to say that a large fraction of your mass is energy stored in the gluon field and in confined motion inside nucleons. That statement does not require a metaphor, and it does not require exaggeration. It follows from measured quark masses, measured proton mass, and the QCD mechanism that connects them. If gluons are massless, how can they contribute energy without rest mass? The answer is that energy is not limited to rest mass. Even for familiar objects, motion contributes to energy. A moving baseball has kinetic energy, even though its rest mass is unchanged. The difference in the proton is scale and confinement. The motions and fields inside the proton are so intense, and the region is so small, that the stored energy is comparable to what we call mass on the outside. The proton is a bound state, where the internal energy budget is the main budget. Another challenge is even sharper. If the gluon is massless because gauge symmetry forbids a mass term, why do we not observe gluons traveling freely like photons? Here, the strong interaction shows its unique character. Photons do not carry electric charge, so they do not strongly interact with each other in everyday conditions. Gluons carry color charge, and that makes gluon fields self-interacting, which leads to confinement. The same structural feature that keeps the theory consistent also creates a world where gluons are permanently tied to hadrons. In this sense, massless and confined are not in conflict. They are parts of one coherent framework. You can take this reasoning one step further and connect it to the way cosmology measures ordinary matter. When cosmologists use the cosmic microwave background to infer the baryon density of the universe, they are inferring how much normal matter existed to interact with radiation in the early plasma. The quantity they infer is a mass density, but baryon mass is largely nucleon mass, and nucleon mass is largely QCD energy. That means that cosmological measurements of normal matter density are indirectly measurements of how much strong interaction energy ended up locked inside stable hadrons after the early universe cooled. This is a rare bridge where the physics of femtometer scales affects the mass accounting of the cosmos. There is also a boundary line here that matters for credibility. Gluons explain why baryonic matter is heavy, but baryonic matter is not the dominant mass component of the universe. Dark matter does not participate in the strong interaction, so gluons do not explain dark matter. That separation is not a weakness of the gluon story. It is a clarity point. It tells you exactly what gluons are responsible for and exactly what they are not. Understanding gluons makes the normal matter budget legible, and it also leaves you with a precise reason dark matter must be something else. If you keep only one image in mind from this part, let it be this. A proton is not a static object with mass sitting inside it like cargo. It is a compact region, where fields and motion are locked together so tightly that the energy becomes inseparable from the identity of the particle. Massless gluons are central to that lock, is less than #0. 5# is greater than. They cannot be held in your hand, and they cannot be photographed, but their work is stamped into the mass of every atom and confirmed by the way matter behaves in accelerators and in supercomputers. And there is one more edge of the maze that does not let go. If mass can arise mainly from confined energy carried by massless gluons, what happens when you try to pull that confinement apart And why does the strong force become more stubborn the harder you try to separate what it binds? Part Tro. Why can gluons never escape a proton, no matter how hard we pull? Try to pull a proton apart, and instead of weakening the force inside, it grows stronger, as if the universe has built a lock that tightens when you turn the key. That single fact is the reason gluons never appear as free particles in nature, the reason quarks are never found alone, and the reason the strong force does not behave like any force you experience in daily life. In this part, we stay inside the verified framework of quantum chromodynamics, and we follow the evidence trail that led physicists to one of the most unusual conclusions in modern science: color confinement. Begin with a comparison that is simple but decisive. Gravity and electromagnetism weaken with distance. If you move a magnet away from a paperclip, the effect fades. If you move farther from Earth, gravitational pull decreases. Those behaviors fit the intuition that influence spreads out like light from a lamp, becoming dimmer as you step away. The strong force, the one that binds quarks into protons and neutrons, does not follow that pattern. So Jinghao Ling, 5# is greater than. At very short distances, it can be relatively mild. But as you try to separate quarks, the energy stored between them increases. This is not a stylistic way of speaking. It is a statement about how the underlying field behaves, supported by scattering experiments and by calculations that reproduce hadron properties from first principles. The simplest picture that captures the outcome is a stretched connection. In electromagnetism, field lines radiate outward. In QCD, the field lines associated with color charge tend to bundle. Instead of spreading into space, they form a narrow tube of field energy between quarks. Physicists call it a flux tube. The consequence is immediate. If the tube stays narrow while you pull the quarks apart, the amount of energy grows roughly in proportion to the separation. Pulling does not run out of force. It demands more energy the farther you go. You can pause here and notice how deeply this changes what escape would even mean. For a photon, escape is natural. Photons do not carry electric charge, so in ordinary conditions they do not bind themselves into permanent bundles. A photon can leave an atom, travel across space, and be detected on a sensor. A gluon is a different kind of object. Gluons carry the very charge, they mediate color charge, and that feature makes them interact with one another intensely, is less than #0. 5# is greater than. The strong field does not remain a passive messenger. It is an active participant constantly reshaping itself, constantly feeding back into the interaction. This self-interaction is the seed of confinement. Historically, this idea did not begin as a poetic statement about nature's preferences. It began as an attempt to reconcile data. In the 1960s and 1970s, experiments probing protons at high energies showed that the proton contains point-like constituents, carrying fractions of momentum. That evidence supported a pattern picture and then a quark-gluon description. But even as quarks became a successful way to organize particle families and predict scattering behaviors, something stubborn remained. No experiment ever pulled out a free quark. No detector ever recorded a particle with fractional electric charge, even though quarks carry fractional charge in the theory. That absence was not a failure of instrumentation repeated for decades. It became a feature that demanded explanation. The explanation that survived is confinement. The strong interaction allows quarks and gluons to exist as components of bound states, but it prevents them from existing as isolated free objects under ordinary conditions. When you try to separate quarks, you inject energy into the system. At first, it looks like you might be succeeding. The quarks move apart, and the field between them becomes more energized. But there is a threshold. The energy you are adding does not remain as a clean, stretched connection indefinitely. At some point, the energy concentrated in the flux tube becomes large enough to produce new particles out of the vacuum, specifically a quark and an antiquark pair. The system then rearranges into two bound states instead of one stretched, broken one. You do not get a lone quark. You get two composite particles, each with quarks inside each color-neutral overall. This is where the common misunderstanding needs to be handled carefully. People sometimes hear that quarks cannot be pulled out and imagine a mysterious rule like a prohibition written into the universe. But the mechanism is dynamical. It is a predictable outcome of field energy rising with separation, combined with the fact that energy can convert into particle-antiparticle pairs when concentrated enough. The details are handled by QCD, but the logical shape is the same every time. Add energy, the field responds. Add more energy, the field responds more strongly. Push the system past a critical point, and the energy shows up as new quarks rather than as a clean break. If you want a concrete laboratory setting, imagine high-energy collisions at a particle accelerator. When a proton is smashed hard enough, you do not see quarks flying out like shards from a broken rock. Instead, you see jets, collimated sprays of hadrons. Those hadrons are the visible record of what happened. A quark or a gluon can be struck and can recoil, but it cannot travel freely to the detector. As it moves away from the collision point, the strong field around it reorganizes, and the energy in that field produces new quark-antiquark pairs, forming a cascade that becomes a jet of ordinary hadrons. The detector sees hadrons because hadrons are color-neutral and can exist as free particles. The quark and gluon content is inferred from the jet pattern and from statistical properties that match QCD predictions. It is worth slowing down on one subtle point, because it is where confusion often takes hold. In QCD, the strong force is carried by gluons, but confinement is not the statement that gluons are weak. It is almost the opposite. Confinement reflects the strong force's persistence and its self-interacting structure. The same theory that makes gluons massless also makes the interaction between color charges behave in a way that encourages binding at large distances. At very short distances, the interaction can be weaker, a property known as asymptotic freedom. At larger separations, the effective interaction grows and confinement appears. The phrase asymptotic freedom deserves a short, careful explanation in ordinary language, because it ties directly to the question of escape. In many forces, we assume closeness means stronger interaction. QCD has a region where the opposite is approximately true. When quarks are extremely close together, as in high-energy collisions probing tiny distance scales, the strong interaction becomes easier to treat, as if the quarks are almost free over that short range. That is why deep inelastic scattering can reveal parton-like behavior. But when the system relaxes back to ordinary distance scales inside a proton, the interaction becomes strong again. Escape would require a quark or gluon to move out to large separation, precisely where the binding becomes more severe and where the energy cost rises. This is also where the cosmic spring image becomes useful, as long as we handle it with precision. A spring stores energy when stretched. The more you stretch it, the more energy it holds and the more it resists further stretching. In QCD, the flux tube between quarks stores energy as separation increases. The parallel is not perfect because QCD is a quantum field theory, not a mechanical device. But the key property rising energy with separation is shared. The lesson is not that protons are literally springs, but that the strong interaction makes separation energetically expensive in a way that ordinary inverse square forces do not. Now connect this to gluons specifically. Gluons are not passive threads between quarks. They are the field itself, and they interact with one another. When you stretch the system, you are stretching a network of gluon fields. Those fields respond by concentrating energy, and because gluons carry color, charge their own interactions, help maintain that concentration. This is one reason it is misleading to picture a proton as three quarks held together by a few gluons like rubber bands. The interior is a constantly evolving field configuration, with quark-antiquark pairs appearing and disappearing, and with gluon density changing with the scale at which you probe it. That complexity is not decorative. It is how confinement is realized in real systems. What makes this topic especially satisfying is that confinement is not just a story told in words. It is supported by multiple independent lines of evidence. Scattering experiments revealed jets rather than free quarks. Measurements of hadron spectra align with QCD expectations when confinement is included. Supercomputer calculations in lattice QCD reproduce hadron masses and other properties, and they do so using the same fundamental equations without inserting confinement by hand as an arbitrary rule. When different methods converge like this, it does not prove every detail is finished, but it narrows the range of plausible alternatives. There is also a natural scientific challenge here that deserves to be stated plainly. If confinement is so robust, why do physicists speak about quark-gluon plasma, where quarks and gluons behave as if they are not confined? The answer is that confinement depends on conditions. In the early universe, at temperatures above roughly 2 trillion Kelvin, matter existed in a state where quarks and gluons were not locked into individual hadrons. Heavy ion collisions can recreate tiny droplets of this state for extremely short times. In that environment, the concept of an isolated hadron dissolves, and quarks and gluons move in a collective medium. But even there, as the system cools, confinement returns, and hadrons form. The gluons do not escape into free space. They reappear as part of bound states once the conditions move back into the regime where confinement dominates. That detail matters because it prevents an oversimplified conclusion. Gluons can exist in different regimes. But the question you posed is about pulling a proton apart under ordinary conditions, the kind of conditions in which protons and atoms are stable. In that regime, confinement is the rule that shapes outcomes. You can pump in energy, you can shatter protons in collisions, you can produce enormous showers of particles, but you still do not extract a free gluon that travels to your detector as an isolated particle. Cosmology counts baryonic matter in terms of protons and neutrons. The stability and mass of those nucleons is controlled by QCD. If confinement worked differently, the early universe would have assembled matter differently. Atomic nuclei might not exist in the same form. Chemistry would not be the same. The large-scale universe depends on this small-scale, no-escape rule, because it sets the identity and stability of ordinary matter from the first seconds onward. And now a final push, because this is where the maze tightens. If the strong force becomes stronger with distance, that suggests the proton is not a static object, but a system where the distribution of gluons changes with the scale at which you look. In the next part, the proton stops looking like a compact particle and starts looking like a dynamic weather system, where gluons dominate the momentum at certain scales, and structure becomes a moving target, even in the most ordinary piece of matter you will ever hold. Part 4. Why does the proton behave more like a storm than a solid particle? A proton looks like a single stable particle until you hit it hard enough to reveal that it is a moving, crowded system whose internal weather never settles. That is not a poetic exaggeration. It is the direct lesson of high-energy scattering experiments, where a proton stops behaving like a neat object with 3 identifiable pieces and instead behaves like a dense, shifting population of quarks, antiquarks, and gluons, sharing momentum in patterns that change with the scale of the counted probe. If you have ever pictured a proton as three quarks connected by a few gluons, this part is designed to replace that image with one that matches the data and to do it in a way that stays calm, precise, and readable. The reason the proton can fool our intuition is that it is extraordinarily small, about 1 femtometer across, roughly 10 to the minus 15 meters. At everyday energies, we never resolve that scale, so the proton behaves like a point. But physics has a reliable trick for seeing small structure. If you want to see smaller details, you use shorter wavelengths, and in particle physics that means higher energies. When a high-energy electron scatters off a proton, the electron's wavelength is effectively short enough to sense internal structure. This method, deep inelastic scattering, became decisive in the late 1960s. Presentations reviewing that era describe how the heroic age of deep inelastic scattering opened in 1968 with SLAC mid-electron-proton experiments. The data showed that the proton responds as if it contains smaller constituents carrying fractions of momentum rather than being a uniform ball. Even that first step did not immediately show the storm. It showed point-like scatterers, later associated with quarks, and it introduced a new accounting system. Instead of describing the proton by a fixed internal geometry, physicists describe it by distributions. How much of the proton's momentum is carried by quarks at a given resolution? How much is carried by gluons? How that balance changes as you probe at higher energy. These are called parton distribution functions. If that phrase sounds abstract, focus on the physical meaning. In a collision, momentum must be conserved. Whatever momentum the proton has must be carried by something inside it. In experiment, quarks that interact electromagnetically account for only part of that momentum. The remainder must be carried by electrically neutral partons. A clear consequence is stated in standard summaries of proton structure, where almost half of the proton momentum is carried by electrically uncharged partons, interpreted as gluons. Older CERN documentation, used for collider physics, made the same point quantitatively, reporting momentum fractions with gluons carrying a large share. Now the storm begins to appear when you look at how these momentum shares behave as the probing scale increases. If the proton were a rigid object, its internal momentum pattern would be stable. Instead, as you go to higher energies, the proton's interior becomes more populated. Quarks radiate gluons. Gluons split into quark-antiquark pairs. Those new quarks radiate more gluons, and gluons themselves radiate gluons. This cascading behavior is not a special feature added to make a story interesting. It is how quantum chromodynamics works when you probe shorter distance scales. CERN's own popular descriptions capture the essential mechanism at higher scales. Quarks radiate gluons. Gluons split into quark-antiquark pairs, and the number of partons increases, while each tends to carry a smaller share of the protons. Total momentum. Imagine you take a snapshot of a crowded stadium at low resolution. You might only see large blocks, perhaps 3 obvious sections, and you could mistake it for a simple layout. Then you zoom in. People appear. Movements appear. Small clusters form and dissolve. The stadium was never truly simple. Your instrument was. In proton physics, the zoom is the momentum transfer in the scattering, and as it increases, the proton does not merely reveal more detail. It reveals more activity because the act of probing at that scale is sensitive to quantum fluctuations that are part of the proton's physical state. A major leap in this understanding came from Hera, the electron-proton collider at DESI, which explored deep inelastic scattering at very small values of a parameter called x, which you can think of as the fraction of the proton's momentum carried by the struck parton. At small x, the data showed a rapid rise in gluon and C-quark densities. Reviews of the Hera legacy highlight exactly this, describing a high density of gluons and sea quarks that increases at small x, and noting that observations at Hera led to entire research programs aimed at describing these regimes. The message is consistent across technical and semi-technical sources. When you probe the proton at high energy and small x gluons dominate. This dominance matters for the storm analogy because it replaces a static interior with a scale-dependent one. At moderate resolution, valence quarks can account for much of what you observe. At higher resolution, especially in small x regimes, the proton's interior looks like a dense gluon field with a sea of quark-antiquark pairs flickering into relevance. The proton is not a box with fixed contents. It is a bound state whose measurable structure depends on how you interrogate it. This means the proton changes depending on the experiment. The careful answer is that the proton's quantum state contains fluctuations at many scales, and different experiments are sensitive to different parts of that state. The underlying object is the same. What changes is the effective description, because the strong interaction is scale-dependent. That scale dependence is not a loophole. It is a tested feature of QCD tied to asymptotic freedom and to the way gluons self-interact. To keep this grounded, consider what we can infer directly. When we collide protons at the Large Hadron Collider, we are not colliding two rigid spheres. We are colliding two ensembles of partons whose densities depend on energy. The outcomes of collisions, the rates at which certain jets or heavy particles are produced, depend sensitively on gluon distributions, precisely because gluon-gluon interactions become so common at high energies. This is why collider physics invests heavily in measuring and refining parton distribution functions, and why the proton's storm character is not a metaphor added for outreach. It is the practical reality that determines predictions and uncertainties. There is also a second layer that makes the storm image scientifically productive, and it involves time. A proton at rest has internal energy and fluctuations, but the timescales are tiny. In a high-energy collision, relativistic effects stretch and compress perceptions of time and distance, and the proton appears as a flattened object with partons effectively frozen during the instant of interaction. This is not presented to make things mystical. It is a straightforward consequence of special relativity combined with the short interaction time. It helps explain why partons can behave almost as if they are independent in the collision, even though the proton is a bound state held together by confinement. The sea quarks are a crucial part of this picture because they prevent a simplistic reading. The proton's net properties, like electric charge, come from its valence quarks, but sea quarks, created through gluon splitting, contribute to momentum and to many observed processes. Their existence is not speculative. It is inferred from the measured structure functions in deep inelastic scattering and from a wide range of hadronic processes. In other words, the sea is not optional. It is required by data. At this point, it becomes useful to underline what gluon density means physically. It does not mean gluons are little beads packed in a jar. It means that in certain kinematic regimes, the probability of interacting with a gluon carrying a small fraction of the proton's momentum becomes very high. As energy increases, gluons proliferate. If you keep pushing to smaller and smaller x, the densities rise so sharply that physicists expect a new regime where growth slows because gluons begin to recombine. This is often discussed under the concept of saturation, and it is one of the primary motivations for the future. Electron-ion collider, described as a machine that will take three-dimensional precision snapshots of the protons. Internal structure. Notice what is happening here. A proton, one of the most familiar ingredients of matter, still contains an active frontier. We know enough to say with confidence that gluons dominate at small x, and that the proton's structure changes with resolution. We know enough to reproduce many properties using QCD and lattice methods, but the detailed mapping of gluon distributions in space and momentum and the onset of saturation remain areas where new measurements can sharply improve our knowledge. That is why modern nuclear and particle physics treats the proton as an object with internal dynamics worth mapping, not as a solved case. When early scattering experiments first suggested point-like constituents, it challenged the idea that the proton was elementary. The community then had to build a theory that could explain two facts that seemed hard to reconcile. In deep, inelastic scattering, partons behaved nearly free at short distances. In ordinary matter, quarks are never observed free. This tension was not resolved by an inspirational speech. It was resolved by the discovery of asymptotic freedom in 1973, which showed that the strong interaction becomes weaker at short distances while remaining confining at larger ones. A clear summary of this logic appears in historical discussions of the Nobel-recognized work, emphasizing that the calculations showed quarks are held together strongly at distances comparable to the size of a proton, while behaving almost free at much shorter distances. That one insight allows the proton to be both a storm at high resolution and a stable particle in your hand. If you are listening for a single operational takeaway, it is this. The proton is stable, but it is not simple. Its stability is the result of confinement, and its apparent internal simplicity is an artifact of low resolution. When you probe it at high energy, its interior reveals a hierarchy of activity dominated increasingly by gluons and C-quarks. Is less than #0. 5# is greater than. This is why in high-energy physics, the proton is described statistically, with distributions that evolve with scale, rather than as a fixed mechanical model. The proton's internal momentum can be redistributed through radiation processes. Valence quarks can lose momentum to emitted gluons, and those gluons can create C-quarks. Over time, the momentum carried by the original valence quarks becomes a smaller fraction at higher resolution. CERN's descriptions of proton structure emphasize exactly this redistribution, describing how higher scales bring more gluons and C-quarks with smaller and smaller momentum shares each. That is why a proton at rest and a proton at multi-tera electron volt energy are described differently, even though it is the same object. The result is a proton that is best understood as a dynamic system with scale-dependent structure. It has persistent identity and conserved quantum numbers, but its interior is not a static arrangement. The strong force creates continuous activity, and the gluon field is the dominant medium through which that activity is organized. And if the proton's interior becomes increasingly gluon-dominated as we probe smaller scales, then, in the earliest moments of the universe, when energies and temperatures were far beyond anything inside ordinary matter today, matter looked like before protons existed at all. And how did a quark-gluon ocean cool into the first stable particles? Part Sync. Why did the early universe begin as a quark-gluon ocean instead of particles? If you rewind the universe far enough to the first few microseconds, after the Big Bang, protons simply could not exist. At temperatures exceeding 2 trillion Kelvin, the very idea of a particle, like a proton or a neutron, breaks down, not because physics fails, but because the conditions make such bound structures impossible. In that early moment, matter did not consist of individual particles with fixed identities. It existed as a dense, strongly interacting medium of quarks and gluons, a state known as quark-gluon plasma. This was not an exotic exception in cosmic history. It was the natural starting point dictated by the laws of the strong force. The reason lies in how confinement depends on energy density. Under ordinary conditions, the strong interaction binds quarks together so tightly that they form stable objects such as protons and neutrons. But confinement is not an absolute rule valid at all temperatures. It is a property of the strong force at low energy density. When temperature rises, energy per degree of freedom rises with it. Eventually, the energy available within a small region becomes comparable to and then exceeds the energy that normally keeps quarks confined. At that point, the bound state description stops being useful. The system reorganizes itself into a new phase where quarks and gluons move through a shared medium rather than being locked inside individual hadrons. This transition is not hypothetical. It is a quantitative prediction of quantum chromodynamics, confirmed by numerical calculations and by laboratory experiments. Lattice QCD simulations show that hadronic matter undergoes a transition at temperatures around 150 to 160 MeV, corresponding to roughly 1.7 to 1.9 trillion Kelvin. This transition is not sharp, like water freezing into ice. It is a smooth crossover, meaning that properties change rapidly but continuously. Above this range, the degrees of freedom are best described as quarks and gluons in a collective state. Below it, hadrons dominate. What matters for the early universe is that its temperature during the first microseconds was well above this threshold. The expansion had only just begun. Energy density was enormous. In that environment, attempting to describe matter as a collection of protons would be like trying to describe steam as a stack of ice cubes. The structures simply could not survive. Quarks and gluons were not confined because confinement itself is a low-temperature phenomenon. This conclusion does not rest on a single line of reasoning. It rests on a convergence of independent evidence. One line comes from theory. QCD, when solved numerically on a lattice, predicts the thermodynamic properties of strongly interacting matter as a function of temperature. These calculations show a dramatic change in energy density, pressure, and degrees of freedom near the transition temperature. Above it, the system behaves as a plasma of quarks and gluons. Below it, hadrons emerge as the relevant carriers of energy and conserved quantum numbers. Another line of evidence comes from experiment. Although we cannot recreate the early universe directly, we can recreate similar energy densities in a controlled way. Heavy ion collisions at facilities such as the relativistic heavy ion collider and the Large Hadron Collider compress enormous amounts of energy into tiny volumes for extremely short times. The matter produced in these collisions exhibits collective behavior that cannot be explained as a simple gas of particles. It flows. It responds to pressure gradients. Its effective viscosity is extraordinarily low. These observations are consistent with the formation of a quark-gluon plasma. One of the most important surprises from these experiments was that the plasma is not weakly interacting. Early expectations imagined a hot gas of nearly free quarks and gluons. Instead, the observed behavior resembles that of a strongly coupled liquid. This matters for cosmology because it suggests that the early universe was not a chaotic collection of independent particles, but a dense, interacting medium with collective properties. In such a medium, energy and momentum were redistributed efficiently, allowing the system to remain close to local equilibrium as it expanded and cooled. Cooling is the next crucial step in the story. As the universe expanded, its temperature dropped. When it passed through the QCD transition range, the balance shifted. Quarks and gluons began to organize themselves into color-neutral bound states. This process is known as hadronization. It did not happen instantaneously everywhere, but it occurred rapidly on cosmic timescales. Within microseconds, the universe transitioned from a quark-gluon plasma into a hadron-dominated state. This moment carries consequences that are still with us. When quarks became confined into protons and neutrons, gluons did not disappear. They became the binding fields inside hadrons. In doing so, they locked a large amount of energy into confined motion and field configurations. That energy became the dominant contribution to the mass of protons and neutrons. In other words, the mass budget of all future atoms was set during this transition. It is important to be precise here. The quark-gluon plasma did not freeze into protons in the way a liquid freezes into a solid. The transition was governed by the changing relevance of degrees of freedom. Above the transition, describing matter in terms of hadrons makes little sense. Below it, describing matter in terms of free quarks and gluons becomes inefficient. The underlying fields remain the same. What changes is how energy is organized. Once protons and neutrons existed as stable objects, the universe entered a new phase of evolution. A few minutes later, nuclear reactions combined these nucleons into light nuclei. Hundreds of thousands of years later, electrons combined with nuclei to form neutral atoms. Billions of years later, stars and galaxies formed. But none of that could have happened without the earlier step, when gluons confined quarks and converted thermal energy into the rest mass of hadrons is less than #0. 5 is greater than. Without that step, there would be no stable nuclei to build chemistry upon. You can see the imprint of this early phase even in modern cosmological measurements. Observations of the cosmic microwave background allow cosmologists to infer the density of ordinary matter in the universe. That density is usually expressed in terms of baryons, meaning protons and neutrons. But when we say we are measuring the amount of baryonic matter, we are effectively measuring how much mass was locked into hadrons during the QCD transition. And as discussed earlier, most of that mass is gluon energy confined inside nucleons. This connection is subtle but powerful. It means that when cosmology counts ordinary matter, it is not merely counting particles. It is counting the outcome of a phase transition governed by the strong force. The early quark-gluon plasma and its cooling history determine how heavy ordinary matter would become long before atoms existed. There is a natural challenge to raise at this point. If quark-gluon plasma exists only at extreme temperatures, how confident can we be that the early universe passed through this phase? The confidence comes from consistency. The temperatures required are precisely those expected from standard cosmological expansion when extrapolated backward using well-tested physics. The properties of the plasma inferred from heavy ion experiments are consistent with theoretical predictions for QCD matter at high temperature, and the resulting hadron masses match what we observe today. No additional assumptions are required. It is also important to emphasize what this explanation does not claim. It does not claim that quark-gluon plasma explains dark matter. It does not claim that QCD alone determines the large-scale structure of the universe. What it does claim is narrower and stronger. It claims that the ordinary matter you see today could only exist because the early universe passed through a phase where quarks and gluons were not confined and then cooled into a phase where they were. In this sense, the early universe did not choose to begin as a quark-gluon ocean. It had no alternative. Given the temperature and density set by the Big Bang, that phase was inevitable. The familiar world of particles emerged only later, as the universe expanded enough to allow confinement to operate. The quark-gluon plasma was not a static background. Its properties depended on time, temperature, and density. The way it cooled and transitioned influenced how smoothly hadrons formed and how energy was partitioned. That process left no direct image, but it left consequences that persist in every proton today. And that leads to a sharp continuation. If gluons were once free to move through a cosmic plasma and later became permanently trapped inside hadrons, how does that trapped energy continue to influence the way cosmologists measure the density of ordinary matter across the universe? Today. Part 6. Why does the density of ordinary matter in cosmology secretly depend on gluons? Cosmologists can weigh the ordinary matter in the universe by studying a faint microwave pattern on the sky. And what they end up weighing is not a pile of protons counted one by one, but the hidden energy inside each proton that gluons keep trapped. That sounds like a trick, but it is an audited trick, repeated across missions, cross-checked against nuclear chemistry from the first minutes, and summarized in numbers precise enough to carry 6 decimal places. The surprise is not that the cosmic microwave background tells us about baryons. The surprise is what baryon mass really means, once you remember where proton mass comes from. In cosmology, ordinary matter usually means baryons, mainly protons and neutrons. Astronomers cannot count those particles directly across the cosmos. They infer their total abundance from the way baryons influence radiation and gravity at early times. The key evidence comes from the cosmic microwave background, the afterglow released when the universe cooled enough for electrons to bind to nuclei and let photons travel freely. The CMB is a map of tiny temperature differences that encodes sound waves that once traveled through the early plasma. Those sound waves were not traveling through empty space. They were traveling through a coupled mixture of photons and baryons, a hot fluid where radiation pushed outward and gravity pulled inward. The patterns we observe today are the frozen record of that competition. Here is the first crucial point. In the early universe, before recombination, baryons contributed inertia to this photon-baryon fluid. More baryon mass means more inertia. More inertia changes how the fluid oscillates. It changes the relative heights of the acoustic peaks in the CMB power spectrum. That is not a vague statement. It is the basis of parameter inference from CMB data. The WMAP team described the goal clearly when interpreting the peaks, noting that the peak characteristics encode parameters including the cosmic baryon density. Planck later refined that inference to sub-percent precision, reporting a baryon density parameter around omega BH² is approximately equal to 0.0224, with tiny uncertainties in the final 2018 cosmological parameters. Results. Now the second point is where gluons quietly enter. When cosmologists infer omega as BH² from the CMB, what is this parameter actually measuring? It is measuring the mass density in baryons, not merely their number density. In other words, the CMB is sensitive to how much weight the baryons add to the early fluid because that weight affects oscillations. But the mass of a baryon is dominated by the internal energy of QCD confinement, and that internal energy is largely carried by gluons and the motion they enforce. So when the CMB constrains baryon density, it is indirectly constraining the cosmic abundance of a form of energy that was locked into protons and neutrons long before atoms existed. It helps to make the logic explicit, step by step, with no algebra. Baryons add mass to the photon-baryon fluid. More mass changes how that fluid responds to radiation pressure. That changes the heights of the acoustic peaks. The peak pattern is observed with high precision. Therefore, the baryon mass density can be inferred. But baryon mass in the physical world is not equal to the sum of bare quark masses. Proton and neutron masses are mostly binding and field energy from the strong force. That energy sits inside the baryons as a permanent contribution to inertia. The CMB does not care whether that inertia came from a Higgs-generated rest mass or from confined field energy. In the equations governing the fluid, inertia is inertia. The oscillations feel the total mass density. That is the sense in which cosmology depends on gluons, even when cosmologists never mention them. You can see why this matters. by imagining an alternate universe that is identical in every way except for QCD. Suppose the strong force produced protons with substantially different masses, while keeping charges and number densities the same. The photon-baryon fluid would have a different inertia. The acoustic peak pattern would shift. The inferred baryon density parameter would be different. You would still talk about omega, b, h squared, but its value would not be the same, because the mass per baryon would not be the same. The CMB is not measuring how many protons exist. It is measuring how much baryonic mass exists, and the conversion between those depends on QCD. This is one of those rare moments in science where a theory about femtometer-scale physics becomes part of the bookkeeping for the largest maps ever made. A proton is about 10 to the power of negative 15 meters across. The CMB anisotropy pattern spans the whole sky, yet the same physical quantity, mass-energy density, connects them. It is not that gluons directly interact with the CMB photons. They do not in any special way. Their influence is indirect and structural. Gluons set the mass of nucleons. Nucleon mass sets baryon inertia. Baryon inertia shapes acoustic oscillations. The CMB records those oscillations. Nothing in this chain is an assumption inserted for narrative convenience. Each link is a standard piece of established physics. To appreciate how clean this inference is, it helps to recall the conditions before recombination. The early universe contained photons, electrons, protons, helium, nuclei, and dark matter. Photons scattered efficiently off free electrons through Thomson scattering, and because electrons are tied to baryons by electric forces, the photons effectively dragged baryons along. That coupling made the photon-baryon fluid behave like a single medium. Gravity from overdensities tried to compress it. Photon pressure resisted. The result was oscillations, compressions, and rarefactions like sound waves. More baryons meant heavier compressions, and that changes the amplitude pattern of peaks in the CMB temperature power spectrum. WMAP's peak interpretation papers emphasize that the peaks arise from adiabatic compression of the photon-baryon fluid in gravitational wells, and that baryon density is encoded in peak properties. Planck then measured those patterns with much higher precision and used them to pin down omega, bh squared, with remarkable accuracy. There is a second, independent way to infer baryon density, and it comes from an even earlier time, the first few minutes. Big Bang nucleosynthesis is the period when light nuclei were formed mainly deuterium, helium-3, helium-4, and lithium-7. The key parameter controlling primordial abundances is the baryon-to-photon ratio, essentially how many baryons existed per photon. Modern reviews of BBN stress that this ratio sets the creation and destruction rates of the light nuclei and remains nearly conserved as the universe expands. If you measure primordial deuterium abundance in pristine gas clouds and compare it with BBN predictions, you can infer the baryon density of the universe. If you then compare that with the baryon density inferred from the CMB, you get a stringent consistency check. The broad result is concordance within uncertainties, and that is one reason cosmologists trust the inferred baryon density so strongly. This is where the gluon connection gains depth rather than being a slogan. The baryon-to-photon ratio is a number ratio. The CMB inference is often summarized as a mass density parameter. Converting between these descriptions requires knowing the mass per baryon, meaning knowing proton and neutron masses. And proton and neutron masses are dominated by strong interaction energy. Gluons, by confining quarks and sustaining intense field energy, set those masses. So even BBN, which sounds like it is just nuclear chemistry, rests on the same QCD foundation, because reaction rates depend on baryon densities and mass scales that include the QCD contribution. This does not mean cosmologists must run a lattice QCD calculation every time they fit Planck data. They do not, because proton and neutron masses are measured with extraordinary precision in laboratories. Cosmology can take them as empirical inputs, but the conceptual point remains. The ordinary matter density that enters cosmological equations is not a count of fundamental particles in the way a chemist counts molecules. It is a mass-energy density of composite objects whose mass is mostly not in their constituent rest masses. The strong force through gluons is the reason that ordinary matter carries substantial mass density at all. If gluons did not do this job, the baryon density parameter inferred from the CMB would describe a universe with far less inertia in its photon-coupled matter, and the acoustic pattern would not match the sky. If the CMB is sensitive to baryon mass density, then is it possible that uncertainties about the internal structure of the proton could affect cosmological parameters? In practice, no, because the proton mass is known to far better precision than cosmological measurements require. What matters is not uncertainty in nucleon masses. What matters is the deeper link between microphysics and cosmology. The CMB can be used as a precision probe of the early universe only because the microphysical inputs are stable and well measured. That stability includes the masses of protons and neutrons, which are stable outcomes of QCD. The success of precision cosmology depends on the reliability of particle physics in ways that are easy to overlook. When the first high-quality maps of the CMB arrived, especially with WMAP, it became possible to talk about precision cosmology with a straight face. Parameter estimation from peak patterns gave consistent values for baryon density, matter density, and other quantities. Planck later provided higher resolution and sensitivity, refining those numbers and tightening uncertainties. The Planck 2018 results summarize this with a baryon density omega ABH squared, quoted around 0.0224, with uncertainties at the level of a few parts in 10,000, depending on dataset combination. Those are not decorative decimals. They are the outcome of a measurement chain that starts with microwave detectors in space and ends with a parameter describing the mass density of ordinary matter. In the background, gluons never appear in the data tables, yet their role is embedded in what the parameter means. This is not an attempt to force gluons into cosmology. It is a reminder that cosmology does not float above particle physics. Cosmology is built from it. When you hear baryon density, you are hearing a statement about the cosmic abundance of protons and neutrons, and therefore about the confinement energy that dominates nucleon mass is less than #0. 5# is greater than. The universe is not just a place where particles exist. It is a place where the internal bookkeeping of those particles shapes the largest observable patterns. There is one more subtle consequence. Because baryon density affects how strongly baryons fall into gravitational wells before recombination, it also influences the contrast and phase of the oscillations. That is part of why the CMB can disentangle baryon density from dark matter density. Dark matter shapes the wells but does not couple to photons. Baryons couple to photons and participate directly in the oscillations. This separation is visible in how peak patterns respond to changing parameters. WMAP papers describe the role of dark matter in enhancing the wells, because it does not scatter off photons or baryons, while the photon-baryon fluid oscillates within those wells. This distinction allows cosmology to infer not just how much matter, but how much is baryonic versus non-baryonic. So the phrase ordinary matter density becomes more precise after this part. It is not simply the density of stuff you can see. It is a parameter inferred from acoustic physics in the early plasma, and it weights the inertia of baryons whose masses are largely confinement energy. The cosmic microwave background in a quiet way, is sensitive to the strong force, not because it sees gluons directly, but because it sees the inertia budget gluons help create, and there is a sharper continuation that follows from this. If cosmology can weigh baryons through the CMB, because baryons add inertia to the early plasma, what happens in the most extreme baryon-rich objects we know, where densities rise beyond nuclei, and the strong force may reorganize matter, again the regime tested by neutron stars. Part-Sept. Why do neutron stars test the limits of gluon physics? A neutron star can carry more than 2 times the Sun's mass and still fit inside a sphere only a few tens of kilometers across. And that single fact forces gluon physics out of textbooks and into the sky. In that volume, gravity is not negotiating. It is compressing matter beyond the density of atomic nuclei, and the only thing that can hold the star up is pressure created by the strong interaction, meaning quarks and gluons, operating in regimes we cannot reproduce for more than an instant on Earth. Neutron stars are not just dense stars. They are laboratories where the internal rules of protons and neutrons and the way gluon fields behave when matter is squeezed to extremes determine whether the star lives as a neutron star or collapses into a black hole. To see why gluons matter here, it helps to begin with a number that has become a kind of boundary marker. We have neutron stars with masses close to, and in some cases above, 2 solar masses. Those measurements are not casual estimates. They come from precise timing of pulsars in binary systems, where relativity shapes the arrival times of radio pulses, and effects like Shapiro delay let astronomers infer the mass. A particularly important case is the millisecond pulsar PSRJ 740 plus 6,621 of the most massive neutron stars with a well-constrained mass, and it has also been studied for its radius using NASA's NISA instrument. NISA analyses report a radius on the order of about 13–14 kilometers for this object, with stated uncertainties that depend on modeling choices. Now pause and take that in with the simplest physical comparison. If you place around 2 solar masses into a sphere with a radius of roughly a dozen kilometers, you are in a regime where the average density is beyond anything in ordinary matter, and the central density can climb several times above nuclear saturation density. NISA-related analyses explicitly discuss constraints in the range of about 5 to 5 times nuclear saturation density when combining pulsar mass and radius information with gravitational wave constraints. In that environment, you cannot pretend that neutrons are rigid marbles packed together. You must ask what a neutron is under compression, what forces act between neutrons at a few femtometers, and how the strong interaction rearranges itself when the spacing between particles becomes comparable to the size of the particles. That is where gluons enter, not as an optional detail, but as the source of the relevant pressure. A neutron is not a featureless object. It is a bound state of quarks held by gluons. Its mass is mostly confinement energy, and its internal structure is dynamic. In a neutron star, those bound states are pushed into close contact. The system is not allowed to ignore the internal physics of nucleons, because the overlap of wave functions and the short-range components of the strong force become unavoidable. The star's stability depends on an equation of state, a relationship between pressure and density. That equation of state is not chosen for convenience. It is what nature uses to decide how matter responds to being compressed. A clean way to state the central challenge is this: gravity supplies compression. Pressure supplies resistance. If the pressure rises fast enough with density, the star can hold itself up. If the pressure rises too slowly, gravity wins, and the star collapses. The pressure comes from several sources, and at neutron star densities, the strong interaction is one of the dominant ones. Degeneracy pressure matters, but it is not the full story. The strong force changes how particles pack, how they repel at short distance, and what new particles may appear when the Fermi energy becomes large enough. When you hear strong force in this context, think of gluons shaping the interaction between quarks, which then manifests as nucleon-nucleon forces and many body effects in dense matter. At densities near nuclear saturation, nuclear physics provides constraints from laboratory experiments, nuclei, and scattering. But neutron stars push beyond that. The matter is cold by particle physics standards, but it is extraordinarily dense. This is a difficult combination. You cannot simply take high-temperature quark-gluon plasma results from heavy ion collisions and paste them into a neutron star model. You also cannot assume ordinary nuclear matter remains unchanged as density rises several times above nuclear saturation. The result is a frontier problem with direct observational consequences. Here, the story takes a historical turn that makes the present measurements feel earned. In the 1930s, Walter Baade and Fritz Zwicky proposed the idea of neutron stars as remnants of supernovae long before anyone had observed one. Decades later, in 1967, Jocelyn Bell Burnell and Anthony Hewish discovered pulsars, and those regular radio pulses were soon understood as rotating neutron stars. That was the first time neutron stars stopped being a theoretical idea and became an object you could time with a clock. From that moment onward, neutron stars became tools. If you can measure their masses and later their radii, you can work backward to constrain the equation of state. You can ask which kinds of matter are possible at the core. This is where the two-solar mass boundary becomes so powerful. Any proposed equation of state must allow a stable neutron star up to at least that mass, because such stars exist. If a model predicts that dense matter softens too much, lowering pressure so that maximum masses are below what we observe, that model is in trouble. This is one of the reasons massive pulsars are not just record holders. They are tests that eliminate entire families of theoretical possibilities. Now add gravitational wave astronomy, because it changes the test from a single number to a dynamic measurement. In 2017, LIGO and Virgo detected the gravitational wave signal GW170817 from a binary neutron star merger, and it was accompanied by light detected across the electromagnetic spectrum. The LIGO press release summarizes the essential sequence, noting that gravitational waves were detected for about 100 seconds, and that a gamma-ray flash was seen about 2 seconds after the gravitational wave signal. That event did not just confirm that neutron star mergers happen. It allowed measurements of tidal deformability, meaning how easily a neutron star's shape is distorted by its companion's gravity during inspiral. Tidal deformability is important because it depends on the internal stiffness of matter. A star with a larger radius and a softer equation of state will deform more. A more compact star with a stiffer equation of state will deform less. LIGO and Virgo analyses of GW170817 produced constraints on these tidal effects, often summarized through parameters that set bounds on how deformable the stars could have been. A representative discussion notes that GW170817 placed an upper limit on the combined tidal deformability in the low-spin case, with values often quoted in the literature as being constrained within a certain range at stated confidence levels. The exact numbers depend on assumptions, but the essential point is stable gravitational waves carry information about neutron star structure, and that structure is determined by the equation of state, which in turn depends on strong interaction physics. NICER then adds another kind of measurement, complementary rather than redundant. NICER observes X-rays from hotspots on rotating neutron stars. Because the star is compact, its gravity bends light strongly, and because it rotates, the hotspot signal is modulated in a way that depends on mass and radius. By modeling the pulse profile, NICER can infer mass-radius constraints. In the NICER analysis of PSR J740 plus 6,620, the reported circumferential radius falls around 13-14 kilometers, again with uncertainties, and the paper explicitly combines this information with gravitational wave constraints to discuss matter at multiple times. Nuclear saturation density. This is exactly the regime where gluon physics is no longer a background assumption. It is the mechanism setting pressure. Now, what is the pressure in physical terms at those densities? There are competing possibilities, and this is where the science stays challenging without becoming speculative. One possibility is that matter remains largely nucleonic, meaning mostly neutrons, with a small fraction of protons and leptons to maintain charge neutrality and beta equilibrium. In that case, the strong interaction between nucleons, including repulsive components at short range and many body forces, provides stiffness. Another possibility is that new degrees of freedom appear. Hyperons may form, or meson condensates, or a transition to deconfined quark matter in the core. Each of these changes pressure. Most of them tend to soften the equation of state, unless additional repulsive interactions counteract the softening. The two solar mass observations then become decisive. If your model introduces new particles that reduce pressure too much, it may fail to support a sufficiently massive neutron star. This is where gluons become the controlling factor again, even if you never say the word in a telescope proposal. If a neutron star core transitions toward deconfined quark matter, then pressure is no longer mainly nucleon-nucleon. It becomes quark matter pressure shaped by QCD interactions among quarks and gluons. Even if the matter remains confined, gluon physics still controls the effective forces between nucleons at short distances, because nucleons are not fundamental, they are composite, and the residual strong force is an emergent effect of QCD. Either way, the path runs through gluons. It is useful to add a practical observational detail here because it shows how these ideas are actually tested. Mass measurements restrict the maximum mass. Radius measurements restrict compactness. Gravitational wave tidal deformability restricts how easily the star deforms. Together, these begin to carve out a narrow region of allowed equations of state. The NICER radius results for PSR J740 plus 6,620 explicitly connect to these multi-messenger constraints, including tidal deformability constraints from gravitational wave events, and discuss matter at several times. Nuclear saturation density. The better these measurements become, the less freedom theorists have to adjust the microphysics arbitrarily. There is also a behind-the-measurement story that matters for keeping this grounded. Gravitational wave signals do not arrive labeled with equation of state. The inference is statistical. It depends on waveform models that incorporate relativistic dynamics and on how tidal effects enter the phase evolution. NICER pulse profile modeling depends on geometric assumptions about hotspot shapes and emission patterns, and on relativistic ray tracing in strong gravity. These are difficult analyses, and the conclusions are reported with uncertainties for good reason, but the direction is clear. Multi-messenger astronomy is turning neutron stars into precision tests of dense QCD matter. A listener might ask a sharp question here, and it deserves a careful answer. If QCD is so successful in describing high-energy experiments, why is dense neutron star matter still uncertain? The reason is not that QCD is wrong. The reason is that the relevant regime is non-perturbative. At very high energies and short distances, QCD can be treated with perturbation theory, and predictions are crisp. In cold, dense matter, at a few times nuclear saturation density, the coupling is strong. Many body correlations matter, and direct calculations from first principles are difficult. Lattice QCD powerful at finite temperature, faces severe challenges at finite baryon density because of the sign problem. This is a technical limitation, not a conceptual failure. It means neutron stars provide data in a region where theory cannot yet compute with full control. That difficulty is exactly why neutron stars test the limits of gluon physics. They put real astronomical boundary conditions on what QCD must allow. A stable 2-solar mass neutron star says the pressure at several times nuclear saturation density cannot be too low. Tidal deformability constraints say the star cannot be too large and deformable. NICER radius constraints say it cannot be too small or too large, beyond certain ranges depending on the object and analysis. These are not philosophical statements. They are the beginnings of an empirical map of dense matter drawn with telescopes and detectors rather than particle beams. It is also worth connecting back briefly to the earlier parts without repeating them. In earlier parts, gluons shaped the mass of protons and neutrons. Here, gluons shaped the pressure response of matter made of those nucleons under extreme compression. In one setting, gluon confinement energy determines the inertia of ordinary matter. In the other, gluon-mediated interactions determine the stiffness that resists collapse. The same microphysics appears in two different roles. That is the unifying logic, and it is why a video about gluons can remain fully relevant even when the scene shifts from a proton's interior to a star. GW170817 showed that neutron stars merge, radiate gravitational waves, and produce electromagnetic light detected by NASA and others, providing a multi-messenger dataset with timing and spectral information. NICER showed that X-ray pulse profiles can constrain radii for massive neutron stars. LIGO and Virgo analyses showed that tidal effects in gravitational waves constrain neutron star deformability, and therefore the equation of state. These are three independent windows converging on the same question: how does matter behave when gluon physics is pushed beyond the regime of normal nuclei? If gluons dominate the mass and the pressure of baryonic matter, then why do they still fail to explain the largest missing mass in the universe, the dark matter that shapes galaxies without ever participating in the strong force? Part Wit. Why don't gluons explain dark matter even though they dominate normal mass? If gluons are responsible for most of the mass in every proton and neutron, then the most unsettling possibility is that we have been staring at the answer to dark matter all along and somehow missing it. But when you follow the evidence that built modern cosmology, gluons become something sharper than an answer. They become a boundary. They explain why ordinary matter is heavy, and at the same time they clarify why ordinary matter, no matter how you rearrange it, cannot supply the missing gravity that shapes galaxies and clusters. This part is about that boundary and why it holds up under multiple independent tests. Start with what cosmology actually measures. When the Planck mission analyzed the cosmic microwave background, it did not simply announce that the universe contains matter. It separated matter into components that behave differently. In the standard interpretation, Planck's final results give a physical baryon density around omega, Bh squared, is approximately equal to 0.0224, and a physical cold dark matter density around omega, Ch squared, is approximately equal to 0.12. Those two numbers are not cosmetic. They mean the gravity budget required to fit the microwave sky has a dominant matter component that is not baryonic. If you translate that into the more familiar percentage language used in mission summaries, the conclusion is that ordinary matter is only about 4.9% of the universe, while dark matter is about 26.8%. Now hold that next to the gluon fact you have already built in earlier parts. Most of the mass of ordinary matter comes from strong interaction energy inside nucleons. That is true. But the Planck numbers are not asking why baryons are heavy. They are asking how much gravitationally active mass exists in total, and how that mass behaves during the formation of structure, and during the era when the CMB pattern was set. The key point is that gluons, however dominant they are inside baryons, do not create a new category of matter separate from baryons. They are part of baryonic matter. If you try to make dark matter out of gluons, you are still trying to make dark matter out of baryons. That boundary becomes obvious as soon as you ask a practical question. What would gluon dark matter look like in the universe? Gluons are not found as free particles under ordinary conditions because of confinement. They live inside hadrons and interact strongly. If you want a cosmic reservoir of gluons large enough to replace dark matter, you would have to hide an enormous amount of baryonic mass in some form that does not emit or absorb light in the usual way. But baryons are not quiet by nature. Baryons couple to electromagnetism through their charged components, through electrons, through plasma physics, through atomic transitions, through radiation pressure, through collisions, through heating, through cooling. Even when baryons are cold, they leave signatures in absorption and emission. Even when they are not radiating strongly, they interact and clump differently from collisionless matter. This is where the cosmic microwave background already provides a strict constraint without needing any later astrophysics. The CMB encodes how much baryonic inertia existed in the photon-baryon fluid before recombination. That inertia changes acoustic peak heights, and that is why omega, BH squared, can be inferred separately from omega CH squared. If you tried to replace the cold dark matter component with more baryons, the peak pattern would change in ways that do not match the observed sky. You can attempt to adjust other parameters, but the fit is not free to move arbitrarily. The CMB is not only a snapshot of density, it is a snapshot of dynamics, and baryons and collisionless matter do not drive the same dynamics. There is a second boundary marker that does not rely on early universe inference at all. It relies on geometry in the nearby universe. The bullet cluster is a collision between two galaxy clusters, where the hot gas, which contains most of the ordinary matter in the clusters, is slowed down by electromagnetic interactions and remains near the collision center, while the dominant mass, inferred from gravitational lensing, is offset and stays aligned with the collisionless components. NASA's dark matter summary emphasizes the bullet cluster as direct evidence describing how observations revealed the separation between where the mass is and where most of the visible X-ray emitting gas is. Chandra's bullet cluster educational material describes the same core point in a particularly crisp way, explaining that lensing shows most of the mass in regions clearly separate from the normal matter traced by hot gas. This separation matters for gluons, because gluons are inseparable from the baryonic sector. If the missing mass were actually baryonic matter, especially in a form dominated by the strong interaction, it would behave like matter that collides, shocks, heats, radiates, and slows down in cluster collisions. The bullet cluster shows a dominant mass component that behaves as if it is largely collisionless during the interaction, passing through without the same kind of drag experienced by the gas. You do not need to know the details of lensing reconstruction to absorb the logic. When two clusters collide, the hot gas lags because it interacts. The galaxies mostly pass through because they are sparse. The gravitational potential peaks, inferred from lensing, track the collisionless component rather than the gas. That is hard to reconcile with a universe where the missing mass is simply more normal matter hidden somewhere, whether or not you choose to describe that normal matter's internal mass as gluon energy. So the boundary line becomes clearer. Gluons dominate the mass of what you can touch because they dominate the internal energy of protons and neutrons. But dark matter, by the best current evidence, is not made of protons and neutrons in any hidden configuration large enough to account for the missing gravity. This is not a statement of preference. It is a statement that follows from at least two independent observations: the early universe acoustic pattern and the behavior of matter in violent cluster collisions. Perhaps dark matter is baryonic, but arranged in compact objects that do not radiate like black holes or faint remnants, so that they behave effectively collisionless and avoid the gas physics. This idea has been explored for decades under many names, and it runs into multiple constraints across astrophysics. Even without reciting a full catalogue, the conceptual issue remains. Baryonic matter participates in ordinary physics during the early universe, including coupling to radiation through charged particles. That coupling is what the CMB is sensitive to. So even if baryons later hide inside compact objects, their presence earlier would still have altered the CMB-inferred baryon density. Planck's separation between omega BH squared and omega CH squared is telling you that the dominant matter component needed to fit the early universe was not in the photon-coupled baryonic sector. This is why the phrase "gluons are a boundary line" is not rhetorical. Gluons explain the mass of baryons without requiring baryons to be numerous enough to become the dominant matter component. They explain why the 4.9% ordinary matter is heavy. They do not help you turn 4.9% into 26.8% without breaking other measurements. At this stage, it helps to say explicitly what dark matter is required to do, because this clarifies why strong interaction physics is the wrong tool for the missing mass problem. Dark matter must gravitate. It must help form the scaffolding for galaxies and clusters. It must not couple strongly to photons, otherwise it would have left obvious radiation signatures. It must not behave like a collisional fluid in events like the bullet cluster, otherwise its mass distribution would trace the shocked gas. These are behavioral requirements, not particle labels. The strong force is a collisional interaction at the scales relevant for baryons. If dark matter felt the strong force in the way baryons do, then on cluster scales it would not remain quietly offset and collisionless through cluster collisions. The observational pattern would not match. There is also a precise reason gluons cannot simply float free to become a diffuse dark matter component. Confinement prevents isolated gluons from existing as stable, long-lived particles moving through space under ordinary conditions. If you deposit energy into QCD matter, attempting to free color-charged objects, the system tends to fragment into color-neutral hadrons. This is why particle colliders observe jets of hadrons rather than streams of isolated quarks and gluons arriving at detectors. A cosmic sea of free gluons is not a stable configuration at low temperature and density. It would hadronize. It would become baryonic matter, with all the electromagnetic consequences that follow. So when you ask why gluons do not explain dark matter, the answer is not that gluons are unimportant. It is that gluons are too tightly tied to the sector we already see and measure as ordinary matter. They dominate normal mass inside nucleons, and that normal mass is already counted by the cosmological baryon density constraints. The missing mass is a separate budget item with different dynamical behavior. A productive way to keep the mind focused here is to separate two ideas that sound similar but are not. One is the origin of mass for ordinary matter. Gluons dominate that. The other is the abundance of matter in the universe. Dark matter dominates that. The first is a microphysics question. The second is a cosmic inventory question. The CMB, gravitational lensing and cluster collisions, tell us that the cosmic inventory has a large non-baryonic component. Gluons are central to the first question, but do not solve the second. There is still an important payoff for a gluon-focused series, because the boundary is not a dead end. It tells you where to stop applying one kind of physics and where to start applying another. It tells you that a complete understanding of ordinary matter requires QCD, while a complete understanding of the dominant matter component requires new physics beyond the standard model, or at least beyond the baryonic sector. That is not a claim about which candidate is correct. It is a claim about what the evidence demands. And there is a practical, modern consequence. The same observational tools that measure dark matter also sharpen the meaning of baryonic matter. When ESA mission summaries say ordinary matter is about 4.9% and dark matter about 26.8%, they are implicitly distinguishing the matter that participates in strong and electromagnetic interactions from matter that does not. Gluons live entirely on the ordinary side of that line. That is why they are so important for explaining the mass of atoms, and why they cannot be invoked to explain the missing gravity that shapes the largest structures. To keep this grounded, return briefly to the most measurable statement. Planck's final cosmological parameter paper reports omega BH squared is approximately equal to 0.0224, and omega.ch squared is approximately equal to 0.12. These are not philosophical numbers. They are the outcome of fitting a physical model to a microwave sky map. They tell you that even if every baryon's mass were entirely gluon energy, and even if you fully understand that mechanism, you still have not created the extra matter required by the CMB fit. The missing component is not a misunderstanding of baryonic mass. It is an additional component with different behavior. There is one more delicate point worth stating with care because it prevents a common confusion. Sometimes people hear that gluons are massless and conclude gluons therefore cannot contribute to gravity. That is not correct. Massless fields carry energy and momentum and therefore gravitate, but that is not the issue here. The issue is not whether gluon energy gravitates. It does. The issue is where that gluon energy resides. In our universe, it resides inside baryons, and the total baryonic budget is measured independently and found to be too small to account for dark matter. This is why the story remains compelling even when it says no. It clarifies the division of labor in the cosmos. Gluons explain why ordinary matter has the mass it has. Dark matter explains why galaxies and clusters have the gravity they have. The two are not interchangeable. And now the continuation can tighten again, because the next step is not about the sky, but about computation. If gluons cannot solve dark matter, yet they still control the mass of every proton we use to measure ordinary matter, then how did physicists prove this mass origin, quantitatively turning QCD from a qualitative explanation into numbers that match the measured proton mass using nothing but supercomputers and first principles calculations? Part Neuf. Why did it take supercomputers to prove where proton mass really comes from? The most unsettling detail about the proton is that its mass is not sitting inside it like a stored ingredient list, and proving that fact required computers powerful enough to simulate a universe in miniature. Physicists had measured the proton's mass with exquisite precision for generations, and they had a theory, quantum chromodynamics, that explained the strong force with striking success in high-energy experiments. But there was a hard gap between we believe QCD is the correct theory and we can start from QCD and calculate the proton's mass from first principles with controlled errors and get the right number. That gap is exactly where lattice QCD enters, and exactly why supercomputers became part of the proof. To understand why brute computing power was needed, hold one simple contrast in mind. At very high energies, QCD becomes weaker in a specific technical sense, and calculations can be done using expansions that behave well. At energies around the proton mass scale, the strong force is strong. The physics is collective. The field lines do not behave like a small correction. They dominate. That is why, as CERN Courier put it, At energies of the order of the proton mass, the equations can only be solved by large-scale computers. This is not a slogan. It is a statement about the failure of a comfortable toolset. Pencil and paper approximations that work for atoms or for weakly interacting fields do not smoothly extend into the non-perturbative regime of confinement. The proton is not a static object made of three quarks arranged like beads. In QCD, it is a bound state formed by quarks interacting through gluon fields that fluctuate constantly. Those fluctuations include C-quark-antiquark pairs, and the gluon field itself carries energy and momentum. Earlier parts of this series leaned on a key conclusion that the proton's mass is mostly not the rest mass of its quarks. The part that still needed proof in the strictest sense was to demonstrate this within QCD itself, rather than inferring it indirectly from experimental patterns and qualitative arguments. The challenge is that QCD is a quantum field theory. Its predictions are at the deepest level averages over an enormous space of possible field configurations. In the regime of confinement, there is no single dominant configuration that you can write down and treat as a small perturbation away from the truth. Instead, you must sample that configuration space in a controlled way, keeping track of how quarks propagate through a fluctuating gluon field and how those fluctuations build a stable bound state with a definite mass. Lattice QCD is the technique that made this possible. The core idea is conceptually simple and technically brutal. You represent space-time not as a smooth continuum, but as a grid of points separated by a small spacing. You then place the QCD fields on that grid in a way that preserves the essential symmetry structure. You compute correlation functions quantities that encode how a proton-like excitation created at one point on the lattice is related to one detected later. From the rate at which those correlations decay with Euclidean time, you extract the mass of the lowest energy state with the proton's quantum numbers. This is not a toy model. It is QCD itself, written in a form that allows numerical evaluation. Why does a grid help? Because it turns an impossible infinite-dimensional integral into a calculation with finitely many degrees of freedom. But finite here does not mean small. A realistic lattice QCD calculation of hadron properties involves 4 dimensions, 3 of space and 1 of time, with enough lattice points to keep finite volume effects under control and a spacing small enough to approach the prots. Continuum limit. Every improvement, a finer grid, a larger volume, quark masses closer to their physical values, makes the computation vastly more expensive. This is the first reason supercomputers were required. The second reason is noise. Proton observables, especially those involving gluon operators, are notoriously difficult to compute because the signal can be small compared to statistical fluctuations, and because renormalization and operator mixing must be handled carefully. There is a world of difference between computing that a proton exists with roughly the right mass and computing a quantitative decomposition of the proton's mass into contributions associated with quark energy, gluon field energy, and the proton trace anomaly, all within a consistent scheme. The 2018 Physical Review Letters paper by Yibo Yang and collaborators is an example of the latter, reporting proton mass decomposition from the QCD energy momentum tensor with non-perturbative renormalization. If you read the abstract of that work slowly, you can hear the checklist of what makes the result credible. Multiple lattice spacings are used, so the calculation can be extrapolated toward the continuum. Multiple volumes are used to control finite size effects. Pion masses, including the physical pion mass, are included, so the result is not a fragile extrapolation. Non-perturbative renormalization is applied to put quark and gluon contributions on the same footing. This is what the word prove means in this context. Not a philosophical proof, but an evidence chain with explicit control of systematic errors. The headline outcome is not that quarks contribute something and gluons contribute something else. The deeper outcome is that you can compute these contributions within QCD and see that gluon field energy and related non-perturbative effects dominate over the direct contribution from quark masses. In the Yang et al. 2018 analysis, quark energy and glue field energy are reported as comparable large fractions, and the trace anomaly contributes a substantial share, while the scalar condensate contribution from light quark masses is much smaller. Different decompositions and schemes can shift the precise numerical partition, but the broad qualitative conclusion remains stable across modern lattice studies and reviews. The proton's mass is largely emergent from QCD dynamics, not a simple sum of quark rest masses. There is an historical reason this took so long. QCD as a theory was established in the 1970s, but early lattice calculations were limited by hardware and algorithms. To do from scratch hadron masses, you need to include the effects of C quarks, not just valence quarks moving in a fixed background. You need gauge configurations generated with dynamical fermions, and you need statistical sampling large enough to reduce uncertainties. The jump from early exploratory lattice studies to precision calculations required decades of advances, not only in computer speed, but in methods, improved actions, better solvers, better error analysis, and access to leadership class computing facilities. This is where the phrase supercomputers proved it can be misunderstood, so it deserves careful framing. The computation does not replace experiment. It connects experiment to theory with a chain that would otherwise be broken. We already knew the proton mass by measurement. We already had many indirect reasons to believe it came mostly from confinement energy. The supercomputer era allowed a third statement, that if you take QCD as written, discretize it on a lattice treat quark masses realistically, and evaluate the quantum averages, numerically the mass of the proton emerges with the correct value, and the internal mass budget points strongly to gluon and known perturbative contributions as dominant. A useful way to picture the work without relying on equations is to imagine a massive bookkeeping exercise where every possible flicker of the gluon field is a ledger entry. The proton is not one configuration. It is the stable statistical outcome of an astronomically large ensemble of configurations. Lattice QCD is the method that generates and samples that ensemble then measures how a proton-like signal behaves across the lattice. Each run produces numbers with statistical uncertainty. Repeating the sampling reduces noise. Varying lattice spacing and volume allows extrapolation to the physical limit. What the supercomputer buys you is the ability to perform enough of this bookkeeping to make the final number meaningful. The US QCD collaboration's planning documents emphasize why dedicated computing resources are needed, because lattice QCD sits at the intersection of demanding physics goals and computational intensity. Their reports describe lattice QCD as a central tool for calculating non-perturbative QCD quantities relevant to nuclear and particle physics priorities, and they outline the scale of computing required to reach precision goals over multi-year horizons. This is not marketing. It is an institutional recognition that the strong force at the proton scale is a computational problem as much as a conceptual one. The Science magazine article, "At Long Last Physicists Calculate the Proton's Mass," captures the human side of this gap between having the correct theory and being able to extract the number. It describes how even with the best computers, it took time for theorists to perform reliable calculations from the underlying description of QCD that match the observed proton mass. That kind of article matters because it conveys an important discipline. In physics, being confident that your theory is correct is not the same as being able to compute everything you want from it. When the coupling is strong, nature does not offer easy shortcuts. There is also a subtle scientific payoff that goes beyond the proton's mass itself. Once you can compute hadron masses from QCD, you can compute many related quantities: sigma terms, form factors, momentum fractions, and operator matrix elements that connect to experiments in scattering and in searches for physics beyond the standard model. Workshops and reviews on proton mass and nucleon structure routinely emphasize that the operators involved are calculable in lattice QCD, but require careful renormalization and high statistics. In other words, the same computational machinery that clarifies the proton mass also becomes a bridge to broader nuclear physics and even to cosmological questions where nucleon properties enter. If lattice QCD uses a grid, doesn't that mean it is an approximation? Yes, it is an approximation at any finite lattice spacing and finite volume. The credibility comes from the way the approximation is controlled. You do calculations at multiple lattice spacings and volumes, then extrapolate to the continuum and infinite volume limits, and you quantify the remaining uncertainty. The method is demanding specifically because it refuses to hide its approximations. It exposes them, then systematically reduces them. Another question is about what exactly was proven. In modern terms, the strongest statements are about consistency and dominance. The calculations show that QCD reproduces the observed hadron mass spectrum, and that within QCD, the dominant contributions to the proton mass arise from gluon field, energy quark, kinetic, and interaction energy, and anomaly-related contributions, while the explicit contribution from light quark masses is comparatively small. That is the quantitative version of the older qualitative claim that most of the proton mass is not the sum of quark rest masses. Earlier parts explained that cosmological baryon density measurements effectively weigh protons and neutrons, and that most of that weight is QCD energy. The mass of ordinary matter becomes not just an explanatory story, but a calculable outcome of the standard model checked against laboratory measurement and refined by numerical methods that are now part of mainstream physics. That is why the proton's mass, a number you can write on a lab wall, is also a number that reaches into the universe's inventory of ordinary matter. Lattice QCD can show how the proton mass emerges from QCD, but it also reveals how subtle the decomposition is, depending on scale, scheme, and the definitions used for separating contributions. That subtlety is not a weakness. It is a reminder that in quantum field theory, even something as familiar as mass can have multiple layers when you look inside. And now the next continuation can sharpen again. If supercomputers can extract the proton's mass from QCD and show how gluon dynamics dominate ordinary matter, then what changes when we stop talking about the proton as a single object and start talking about gluons as the hidden accountants of the entire visible universe, setting the weight of everything we can build and measure? Part D's. Why does understanding gluons change how we think about the universe itself? The most unsettling realization is that the weight of the visible universe is not set by the things we can list, but by motion we can barely observe. When we say that stars, planets, and people have mass, we instinctively imagine substance ingredients, something solid that adds up. Yet when physicists followed the evidence all the way down to the deepest level we can test, they found that most of this mass is not carried by particles in the ordinary sense at all. It is carried by energy locked into fields. And in the visible universe, the dominant field responsible for that lock is the gluon field of the strong interaction. Understanding this does not merely refine our picture of protons. It quietly reshapes how we understand matter, structure, and the cosmic inventory itself. Begin with a statement that once sounded provocative, but today is grounded in calculation. Frank Wilczek summarized it plainly when he said that mass is mostly energy. This is not a slogan. It is a quantitative conclusion that follows from quantum chromodynamics and from the ability to compute hadron masses from first principles. Earlier parts showed how lattice QCD demonstrated that the proton's mass is dominated by gluon field energy and related non-perturbative effects, not by the rest masses of quarks. That result immediately scales up. Protons and neutrons make up nearly all ordinary matter. Ordinary matter makes up all stars, gas, dust, planets, and every atom in your body. When you weigh the visible universe, you are mostly weighing gluon dynamics. This has a direct cosmological consequence. Measurements of baryon density from the cosmic microwave background, using missions such as Planck, are often described as counting protons and neutrons. In reality, they are sensitive to the inertia of the baryon-photon fluid in the early universe. That inertia depends on the mass of baryons. And that mass, as we now know with quantitative confidence, is mostly gluon energy. Yu Jinghao Ling. 5# is greater than. So when cosmologists fit acoustic peaks in the microwave sky, they are indirectly fitting the consequences of strong force physics, acting inside nucleons long before the first stars formed. This reframes what cosmic mass origin really means. In many popular narratives, the story of mass begins and ends with the Higgs field, and that story is correct within its domain. The Higgs mechanism explains why fundamental fermions and weak gauge bosons have non-zero rest mass. But in the visible universe, that contribution is a small correction. The Higgs gives quarks their bare masses, but those masses account for only a small fraction of the mass of protons and neutrons. The rest comes from confinement from the energy of gluon fields and the motion they enforce. The universe we see is heavy not because its fundamental building blocks are heavy, but because they are bound. Once you accept that the hierarchy of physical theories falls into a clearer order, gravity governs the large-scale architecture of the universe. Electromagnetism governs chemistry, radiation, and much of astrophysical observation. The weak interaction governs certain forms of decay and early universe processes. But the strong interaction through gluons quietly determines how much ordinary matter weighs, how much inertia it carries, and therefore how it responds to gravity on every scale. Without gluons, stars would not be as massive as they are. Galaxies made of baryons would not have the same dynamics. The entire luminous component of the cosmos would be different in a way that cannot be fixed by adjusting a single parameter elsewhere. There is also a conceptual shift here that is easy to miss. Classical intuition treats mass as a primitive property. In modern physics, mass is often an emergent property. In QCD, it emerges from interactions. The proton is not heavy because it contains heavy constituents. It is heavy because the rules of the strong force do not allow its constituents to sit still. They are confined, their fields fluctuate, and the energy of those fluctuations contributes to inertia. When you scale that up to the universe, you find that much of what gravity responds to is not stuff in the everyday sense, but stored energy of interaction. This perspective also sharpens the boundary between what we see and what we do not. In the previous part, gluons were identified as a boundary line separating ordinary matter from dark matter. Now you can see why that boundary is so informative. Gluons explain the mass of ordinary matter completely within the standard model. Dark matter, by contrast, does not participate in the strong interaction. It does not carry gluon energy. Its gravitational influence is therefore not a misunderstanding of baryonic mass, but evidence for a genuinely different component. Understanding gluons removes one possible confusion and makes the dark matter problem cleaner, not more complicated. There is a historical rhythm to this realization that echoes earlier revolutions. In the 19th century, mass and energy were treated as separate conserved quantities. In the 20th century, relativity unified them. In the late 20th and early 21st centuries, Quantum field theory showed that most of the mass we encounter is not rest mass at all, but interaction energy. Each step did not discard the previous one. It refined it. Understanding gluons is part of that refinement. It tells us that the universe's visible weight is a dynamic outcome, not a static inventory. This has practical consequences for how we connect disciplines. Nuclear physics, particle physics, and cosmology are often taught as separate subjects. Gluon physics cuts across all three. The same QCD dynamics that determine the proton's mass also influence neutron star structure, affect the equation of state of dense matter, and set the baryonic inertia that leaves an imprint on the cosmic microwave background. Xiaoyu Jinghao Lin. 5# is greater than when gravitational wave observatories measure tidal deformability in neutron star mergers. They are probing matter whose stiffness is controlled by strong force physics. When cosmologists infer baryon density, they are probing the same physics in a very different regime. This unity is not philosophical, it is operational. Gluons cannot be isolated. They do not travel freely across space in a way we can detect directly. Yet they dominate the mass of everything we can see. They are invisible not because they are irrelevant, but because they are confined. This is a different kind of invisibility from dark matter, which is invisible because it does not couple to light. Understanding that distinction prevents confusion. It teaches us that unseen does not mean unimportant, but it also teaches us that not all unseen things play the same role. One of the most valuable outcomes of this understanding is intellectual economy. Once you accept that gluons account for the mass of ordinary matter, you no longer need to search for exotic explanations for why atoms are heavy. The explanation is already present, tested, and computed. That frees attention to focus on questions that remain genuinely open, such as the nature of dark matter, the origin of cosmic acceleration, and the behavior of matter at densities beyond current experimental reach. Clarity about gluons does not close inquiry. It sharpens it. It is also worth noting what this understanding does not do. It does not diminish the importance of other fields or mechanisms. The Higgs field remains essential for setting the masses of fundamental particles. Electroweak physics remains essential for processes in the early universe. Gravity remains essential for structure formation. Understanding gluons does not replace these. It shows how they fit together. It shows that the visible universe is a layered system, where different interactions dominate different aspects of reality. The visible universe is mostly mass made from energy. That energy is largely stored in gluon fields, confining quarks inside protons and neutrons. Those protons and neutrons make stars, gas, and planets. Their mass shapes how gravity builds galaxies and clusters. Their inertia leaves patterns in the cosmic microwave background, and their limitations mark the boundary beyond which new physics must exist to explain dark matter. None of this requires speculation. It follows from experiments, observations, and calculations that agree across scales. If there is a single change in perspective that understanding gluons demands, it is this. When we ask what the universe is made of, the answer is not only particles, but interactions. Not only things, but the energy that binds them. Thank you for spending this time exploring these ideas, for lending your attention to the quiet mechanisms that shape the cosmos we see. May your thoughts slow, your questions remain curious, and your rest tonight be calm and easy. Sleep well.